much. Thank you very much. I am very glad to be able to talk here before many old friends. And I started my research on electron interferometry 40 years ago, with the aim of realizing electron holography. Which was devised by Gabor as a means to break through the resolution limit of electron microscopes. In 1968, we demonstrated its possibility. We first formed an interference pattern between an object wave and a reference wave called a hologram with electrons. Since all the information is stored, is contained, intensity and phase is contained in the hologram, we can reconstruct the electron wavefronts as optical wavefronts by illuminating a laser beam onto the hologram film. And Gabor intended to optically compensate for the aberrations in the electron lenses. However, the resolution of the reconstructed images did not reach even that of electron microscopes because of the poor coherence of an electron beam. In fact, the exposure time to take one hologram was as long as 10 minutes, and the resolution was only 50 angstrom. So I soon started to develop brighter, coherent electron beams, a field emitted from this pointed tip, which I have been doing ever since. Since the virtual source is as small as 50 angstrom, the beam is susceptible to mechanical vibration of the tip and the beam diffraction due to stray AC magnetic field. And if the point source moves, the beam brightness drops. So we struggle desperately to remove the beam disturbances. After 10 years of work, we had increased the beam brightness by 2 orders of magnitude, thus producing a dramatic effect. We became able to directly observe such interference fringes on a fluorescent screen, which was previously impossible. Electron interference experiments became much easier to carry out. So I wanted to observe the world of quantum mechanics. And since that time, we have attempted various challenging experiments. In effect, vortices, Superconductor. Up to now, I have shown you only interference fringes. However, electrons are also particles. These 2 features of electrons can be demonstrated in a single experiment based on the single electron build-up of an interference pattern. Richard Feynman asserted that this experiment, although the heart of quantum mechanics, is the thought experiment that cannot be carried out in practice. Nevertheless, such an experiment has become feasible thanks to advanced equipment such as extremely stable biprism, electron biprism, and 2-dimensional electron counting system detector with almost 100% detection efficiency. When the electron beam intensity is extremely weak, so that no more than 1 electron can exist in the microscope, electrons appear as spots here and there at random at first. Electrons are thus particles, surely particles. But when we wait for the accumulation of many electrons, something like interference fringes begin to appear. The fringes are formed only when 2 electron waves pass through on both sides of the film, of the biprism filament, and overlap in the lower detector plane. Every time I see this video, I have no choice but to wonder about the mystery of electrons. The AB effect is also so counterintuitive that its existence of a question, thus producing a long controversy. We had to carry out a series of experiments spanning 6 years to obtain unambiguous results everybody accepted. And let's repeat the AB effect. This coil becomes a magnet when a current is applied to it. If it is infinitely long, the north and the south poles are very far apart, so no magnetic field exists outside the coil. 2 electron beams from a point source pass through on both sides of the coil and overlap in the lower plane, forming an interference pattern. Outside the coil, there are no magnetic fields, but there are vector potentials. They circulate and form vortices. The incident electron wavefronts are displaced in the opposite direction by vector potentials on both sides of the coil. In previous experiments, a coil with a finite length was used, and the magnetic flux inevitably leaked out from both ends of the coil. Therefore, the detected AV effect was attributed to the leakage field. Since we cannot make an infinitely long coil experimentally, we use a toroidal coil or magnet to avoid this problem, as C.Z. Cooper suggested. So we bent a coil to form a ring, thus creating an ideal sample with a finite geometry. Magnetic lines are enclosed within the ring and do not leak out. We showed the existence of phase difference between 2 electron waves passing through inside the hole and outside a square toroid. Well, the electrons must have been affected by vector potential. However, some people were still not satisfied because the electrons partially touched and even penetrated the magnet. They claimed that if only part of the wave function touched the magnetic field, the whole wave function should be affected. And C.N. Yang recommended after my talk at ISQM 83 in Tokyo that we use a ring magnet covered with a superconductor. The magnetic flux would then be shielded and enclosed within the superconductor due to the Meissner effect, and thus would not leak out. Under the condition of no overlap between electron waves and magnetic flux, a phase difference was detected, and the quantization of fringe displacement by half a fringe spacing ensures flux quantization and also complete magnetic shielding. In addition, the process of magnetic flux quantization became observable as Professor Yan had predicted. The AB effect, which was thought at first to be a mysterious phenomenon, became one of the most fundamental principles in quantum mechanics, which should appear in any fields. AB effect is practically used to visualize a magnetic line directory. So let's take a look at examples. Here we can see the outline of a cobalt particle revealed by electron microscopy. In this interference micrograph, circular phase contours appear inside the particle. This shows the contours of the wavefront, transmitted wavefront. In 1980, we found that these phase contrasts directly indicate quantitative magnetic lines force in H/E flux units. I was deeply impressed with this beautiful relationship. The sensitivity does not change independent of the velocities of the incident electrons. And let me show you an application to magnetic recording. A magnetic head slides across metal tape, and the bit patterns are recorded as shown. The observed magnetic lines below are exactly like a stream of water, since we are looking at divergence-free B. So two streams of magnetic lines collide head-on here and produce vortices. Magnetic lines meander toward the edge of the tape and then beyond the tape edge, leak outside. We then observed magnetic lines of recording heads. Magnetic lines radially extend from a tiny magnetic head for perpendicular recording. A stronger and yet very localized magnetic field is required for high-density magnetic recording. But we also need a Zeller field, outside Zeller field, occasionally, which poses rather difficulties. The outside magnetic lines cannot be switched off because we cannot make magnetization inside the head. When we optimized the material and the shape, these straight magnetic lines changed into U-turn lines when an external magnetic field is removed. At the pole tip, magnetic lines form a closed circuit. These on and off patterns are both symmetrical. Can you guess how straight lines can be changed into U-turn lines? This change cannot be made while keeping the symmetry. And I'm going to show you how this happens, since it is interesting. Now, when the applied magnetic field is reduced, the magnetic lines begin to bend from the lower left, and the blue bent lines move upward. Why? Red U-turn lines appear from the bottom and push them up, like this. And finally cover the whole region. The blue lines change into a closed circle. The leakage magnetic field gradually decreases and almost vanishes in the remnant state, since all magnetic lines are enclosed within the head, restoring the pattern symmetry. And now let's move on to application result to colossal magnetoresistance, which has just been published in Nature Nanotechnology. In CML, when the magnetic field increases, the resistance decreases. Why? Tiny isolated magnets, ferromagnets, nucleate and grow in the insulating phase, and thus creating conduction path. This happens when the temperature decreases or magnetic field increases. Let me show you this process by electron holography. When we reduce the temperature with no magnetic field, a tiny spot suddenly appeared with bright and dark contrast features in a defocused Lorentz micrograph. This image can be interpreted as a single ferromagnet. After tremor, it suddenly changed into a double domain, which continued to grow and finally coalesced into multiple domains. White and black lines are domain boundaries, but we found two kinds of boundaries, zigzag and smooth. They became more conspicuous as the domain becomes larger. The domain wall inside ferromagnetic phases are all smooth, straight, while the boundaries between the ferromagnetic and the insulating phases are a zigzag. Why? There must be tiny clusters scattered all over the insulating domain that cannot easily become ferromagnetic. The growth of the domains was locally interrupted by these clusters, resulting in a zigzag boundary and its stepwise motion. This was confirmed by electron diffraction. So let me show you a video of this, short video, but low contrast. When we reduce the temperature, a small single magnetic domains were produced, this one and this one. They soon change to double domains. You may have noticed that magnetization direction was not fixed up and down. It was determined spontaneously, and these domains grew and coalesced, forming multiple domains. They grew abruptly from time to time, as if they were a pin. New domains soon began to appear going to the left. The single domain oscillates for a second during magnetization reversal in one half region, and then changes into a double domain. Okay, let's move on to application to superconductors. In superconductors, two electrons are attracted to form a Cooper pair, just like two Japanese coins on water surface. They are attracted. Cooper pairs are both particles and no longer governed by the Paul exclusion principle. So they can condensate into the same state, forming a macroscopic wave. And when the magnetic field is applied to this wave and the magnetic line actually penetrate the wave, its wave is shifted by circulating vector potential, thus producing a vortex. So a vortex in a superconductor is just like a tornado. But the problem is this tornado. The problem is how to observe superconducting vortices. We cannot directly observe supercurrent, but we can observe magnetic lines by using electron waves. And our experiment is as follows. We evaporated a lead film onto the surface of the wire from right-hand side. A magnetic field was applied perpendicular to it. Electrons illuminate the magnetic field from above, and parallel magnetic lines were observed as phase contrast by electron holography. When the sample was cooled below TC, we observed a dramatic change. These parallel magnetic lines were focused at the film surface. So we are observing the spontaneous breaking of the gauge invariance in superconductors. A broad magnetic line becomes narrower to penetrate into the superconductor in a thin filament form. This is because vector potentials circulating around the magnetic line in a vacuum becomes vortex currents in a superconductor. Professor Nambu applied this principle to unify all fundamental forces in nature. Scientists in CERN are now investigating whether this world is truly superconductive or not. Lastly, I'd like to introduce our planning of a new microscope. Number in 83. We want to develop an atomic resolution, ultra high voltage holography electron microscope. And for this purpose, we have to get higher resolution, maybe in the order of 0.1 angstrom, to further increase the beam brightness and to develop an extremely stable specimen stage, since electron holography requires a longer exposure time to take one hologram. And this is a big challenge, technological big challenge, but a new possibility cannot be opened up by starting to tackle the challenge. The funding for this proposal, this one, was once accepted last month, but it is now being re-examined by the new Japanese cabinet of the Democratic Party. So we are worrying about it. And with this microscope, we wish to observe electron wave fronts from each atoms, thus making the 3D observation of atoms possible. In addition, we can observe electromagnetic fields or more exactly gauge fields in atomic resolution. I had wanted to retire until the end of this fiscal year, but if this development is funded by any chance, I want to make efforts again. In that case, I would like to ask you for your kind help. And I want to make a very interesting experiment, fundamental experiments in quantum mechanics also. Thank you very much for your kind attention.
Thank you very much. Time for one or two very quick questions. Anybody? It was a very clear presentation, Dr. Tonomura, and we're speechless. But we all wish you extremely good luck with the new Japanese government. Thank you.
Thank you very much.